Hello, everyone. Welcome to today's Science Talk. I'm delighted to be your host. My name is Dr. Miriam Axel, and I'm thrilled to welcome you today. For those of you joining us for the first time, we're delighted to have you here. I'm pleased to share that all of our previous Science Talks are available online on our website at unu.edu/INWEH/science-talks with an S. Today's talk, like all others, will be recorded, and the recording and video will be made available after the session. I'd like to remind you to please put your questions for our speaker in the Q&A box, and I will make sure to read them out to our speaker at the end of the talk. Today's talk is SeasonNet, a deep learning framework for bias correction and seasonal forecasting model. And I'm delighted to introduce today's speaker, Dr. Rendani Mbuvha, who is an actuary and machine learning expert, specializing in the application of machine learning to improve our understanding of climate-related risks. At UNU-INWEH, he's developing machine learning applications to better predict extreme climate events such as floods, heat waves, and droughts in order to better inform policymaking. Beyond his contributions to UNU-INWEH, Dr. Mbuvha is a senior lecturer, associate professor in actuarial science at the Department of Mathematics at the University of Manchester. Dr. Mbuvha received his PhD from the University of Johannesburg, concentrating on shadow Hamiltonian Monte Carlo methods within Bayesian neural networks. His academic journey also includes a master's in machine learning from KTH Royal Institute of Technology in Sweden. Dr. Mbuvha is the author of Hamiltonian Monte Carlo Methods in Machine Learning. And now, without further ado, I'm delighted to turn it over to you, Dr. Mbuvha.
Thank you, Miriam, for that kind introduction. Today's talk, as you mentioned, is about a deep learning framework, which I'll set a bit of context for before going into the technical deep learning. This is not my work alone. This is joint work between Zahir Nikrafta, my PhD student at Queen Mary University of London, where I was before, Mushtaba Sadeh at Boise State, and Professor Willem Landman at the University of Pretoria, South Africa. I just want to check before I proceed that you can see my slides.
Yes, we can.
Great. All right. So I guess starting with what is more a technical definition of seasonal forecasting. What I like to think of seasonal forecasting as is sort of a forecast that would answer the question, what will the next 3 months / 90 days look like? So in terms of where it lies, in terms of the lead time forecasting spectrum, we're sort of looking at a period of around 90, 100 days, where we've surpassed sort of like the skill that we inherit from autoregressiveness of climate or the sort of persistency of climate phenomena to sort of longer term teleconnection driven sources of forecast skill or accuracy. And what I mean by this is, if you look on the right, there's a nice chart that was created by the Norwegian Meteorological Institute that sort of tells us or sort of gives some sort of ideas on where the skill or the accuracy is coming from, or the source of predictability. And we find that when we're focusing on, say, the next 90 days, what we really are looking at is skill that is driven by sea surface temperature, sea ice balances, and that allows us to then have some idea of what the distribution of certain climatic variables would look like after around with a 90-day outlook or that sort of scale. Before that, you would have the subseasonal scale, which goes anywhere from a month to there. And we always know that there's a loss of forecasting scale in that time frame. But what we'll focus on today is what this what the seasonal or the 90 days or 3 months look like. Often there are physical models that parameterize such phenomena, that tries to extract the physical phenomena that, say, for example, the teleconnections or ENSO oscillations in the Pacific, that sort of tries to then see, can we then have, what will the temperature look like for persisting and transferring the skill from what the sea surface temperatures are suggesting as well as the regular Navier-Stokes types equations to sort of model that phenomena. Like with any climate models, most of the big climate centers would have such a model. And the C3S service, or the Copernicus Climate Change Service, hosts some of the most skillful of the state-of-the-art models from centers such as the UK Met Office, such as including Météo-France and the other big centers. And we're going to work with a couple of these models as we go ahead. Why is this important? Because this is not time scale for me as an actuary as well. I feel like it's a good amount of time in terms of lead time, 90 days to 3 months, that allows one to plan. If you're thinking about water management and water resource management, what river flows are going to look like, what dam levels are going to look like. It allows you to think about public health issues, if you can link rainfall to tropical diseases like malaria. Of course, the big utility of these types of forecasts is in agriculture and food security. But between going from the model to getting to, I guess, your downstream application or your utility element, you have to transfer or train what I call the transfer function. This could be the machine learning that we'll talk about today. It could be linear models that have been previously applied in this area. It could be quantile mapping types methods that have been applied, sort of transfer what, the forecasts to most often what the closest observations or realization was, and therefore also perhaps building that bridge to river flow, stream flow levels, malaria cases, as well as crop yield. But we'll get back to this as well. But as with all physical models, they all have some bias, and the bias here often arises by what I often call, on the right of the slide, some nuances that are there in the physical phenomena that perhaps you cannot model explicitly in a physical system, mainly because sometimes some processes like cloud physics, for example, we don't have a full understanding for those, and it's very, very difficult to resolve in a mesh grid as we're solving our systems of equations in physical modeling, as well as, again, some processes we still don't know how to represent, so we sort of take, again, proxies. And this is best endeavors such that you sort of get to almost the limit in which you can get the physical representation of the process, bearing in mind some constraints on compute, available of compute memory, as well as processing time in terms of getting your forecast out on time. As a result, you'll find that in the green there will be essentially what the forecast would be in terms of the blue there, and what actually your model suggests. And you'll see that there's a bit of drift there. And what we're trying to do here is train models that try and close that gap in terms, essentially, recalibrate empirically or using more non-parametric ways in terms of not representing the physical process, but learning those drifts between what the model suggests and therefore the systematic ones you can bias correct using neural networks such as CISNet, as we'll present later on. Again, one of the things that is a bit of a segue into how we parameterize CISNet and goes into some of the motivations later on, is this idea that because of this time frame and different utility that seasonal forecasts can have, we have to think about what sort of impact one would look at. And a lot of impacts that we think about are more in the disaster risk management that can be more expressed in a way by looking at metrics in terms of skillfulness. When you assess this type of models, when you evaluate them, say, for example, you're looking at flood predictions. You might want to look at not necessarily the idea that you can get the rainfall correct for every day for in a 90-day rollout of a forecast, but you want to look at the distribution over a season. You want to look at how many flood days could you have over that 90 days. If you're looking at a drought perspective, how many dry days would you have? If you're looking at, again, a drought, and even looking at things like wildfire indicators, like consecutive dry days could actually give you an idea of the likelihood of wildfire events. again, there are certain temperatures that are harmful to human life. And therefore, if you then sort of analyze the distribution of what your seasonal forecast gives you for the 90 days and characterize it in metrics or indices that allow you to infer the likelihood of certain high impact and severe events. And that's sort of the lens of evaluation that we'll talk about in this type of work. And I'll show you some initial evaluations of the models themselves and how we incorporate that into SeasonNet. Then the next bit is, well, on the bottom is the traditional assessment. Seasonal forecasts are often synonymous with probabilistic evaluations. In that characterization, again, I mentioned the distribution of things like rainfall in the season. You look at, the total rainfall in a season, and you'll characterize it normally with the triciles that are there at the bottom of the slide, where you're saying is going to be above normal climatology or normal tendency in terms of the total rainfall in that season. Is going to be normal in the middle of the tricile, or is it going to be below? And often then interventions are designed on those triciles. There's lots of questions in the seasonal forecasting community, whether the triciles have as much utility as we'd like to have. And of course, the correlation in terms of what would that be, either being seasonal totals or daily rollouts of how that will work. So those metrics, that are traditionally used, one of the arguments here in terms of designing SeasonNet and our work leading into SeasonNet talks to sort of focusing quite a bit more on the extremes, quite a bit more also on impact-based metrics as we move along. So just a bit on sort of like this impact-based evaluation. I'm just going to segue a bit into how you could do it on a seasonal model. And this is actually output that comes out of a paper led by my PhD student, Diana Crafter, with my collaborator that I've mentioned before. And the reason I put the IPCC regions as part of the slide there is to actually, we use those as our unit, a spatial unit of evaluation. So we're going to calculate all those indices or evaluation metrics across the different regions and use some insights on the frequency of certain extreme events in those regions to tell us how to evaluate and when to evaluate such models for scale. Once we've done that evaluation, we'll have an idea of what models work for bias correction in terms of using neural network architecture like SeasonNet, and then we'll do some other evaluations that are based on impact-based indices as well. So for example, as I mentioned, if you want to look into wildfire-prone regions, for example, if you look at regions such as Northern Australia, as NAU at the top of the slide there, if you look at Western North America, I think we all know what happened recently, and you look at them within their sort of flood-prone and their sort of wildfire-prone time points, and the different seasons for those wildfires sort of occur. And then you take the base models before we even start using deep learning to actually post-process the bias. Look at whether the process representation within the physical models allow you to look at some indices that help you look at the likelihood of wildfires. Here, what we look at particularly is the maximum consecutive dry days with less than 1 millimeter rainfall. And as you can see, in most of this metrics, we go from just pure correlations, Kendall tau, and then we even then look into off the index, not necessarily the time series of precipitation sort of data. And here we're evaluating the models that I've mentioned, the Météo-France model, the ECC model, the German DWD model, and the CMCC models, using error5 as ground truth, and we'll evolve that as we go on. And what we then see is that we see different levels of skillfulness of the models across the different IPCC regions that are wildfire prone in their wildfire seasons. And this can again give you some sort of simple idea, rather than going again over a sort of traditional time series analysis. And we use this as we go into the bias correction as well. And here, what we often see is that the Met Office model and the Météo-France models, including also the DWD model sort of have, even if you look at the Taylor plots, which sort of look at how your standard deviation across both the reference data and what the models are predicting, your correlations, also and how that's sort of across all those dimensions. So the higher in your Taylor diagram, the better your model is. So you really want your model to be somewhere in sort of like, you know, the sort of ideal sort of criterion, and this sort of shows you where that goes. So you don't want to stretch the different exercises. So as you can see, this is one of the evaluations. The next one, if you're thinking about it, is would be then the heavy precipitation days. This is now on the flat side of things. Again, we're looking at precipitation days that exceed 10 millimeters and above the first 75th percent. There's a bit of an end criterion there. And again, these are flood prone regions such as the Southeast East Asian Sea area, a bit of Central Europe as well, in the DJF, in sort of like the rainy winter season there, as well as a few other rainy seasons in South Asia as well. But what we again see is we see that if you look at the first sort of quadrant there at the top, this is more the correlation bits, and then if you look at the percentage bias on in terms of the sort of second part of the plot, you can see that you do have some scale in terms of the Météo-France models. But then again, if you then look at the Taylor diagram, you can then see sort of like the distinguishing factor across the different models. We do something similar as well when we're looking at heavily populated regions. Again, we're looking at impacts both in terms of the extreme events, where they occur and where they frequently occur, and whether the models can capture them right off the box to start with. And then we also looked at just consecutive wet days in regions that are heavily populated and densely populated, because the impact there is just because of the number of lives and assets that are also in those areas. So again, in terms of sort of like following that impact-based framework, evaluating the models, and as you can see here, if you look at the correlations, we have relatively high correlations again in the DWD models. The Météo-France models as well. But if you then look at if you look at how close you get in terms of matching the standard deviation, i.e., the variance that is being captured by the models relative to the variance in the reference data, and actually look at what happens there, you then see again that very close to where the black star is, which is more the reference data. The closest model to that across the correlation standard deviation dimension, you get the UK Met Office models. And then if you consider the multiple criterions again, if you're looking at the Taylor plot, will suggest that again the UK Met Office followed probably again on that scale by Météo-France and that. So this just tries and encapsulates all the three metrics. But again, this is sort of an illustration of how you can evaluate these models, and you can then use them in sort of disaster response management and other similar activity. So not to focus it on impact-based evaluation, but it's a framework that we'll use when we look into our seasonal architecture. We did see that there's some, we evaluated sort of like the scale in relation to floods and wildfires. This varies quite significantly by region, as we would expect. There were some of the results would be in the paper Nakrafta et al. That talks to scale in areas that are more tropical than extratropical. And then again, more generally, if you consider the criterion around bias, which is just the difference between what the predictions on the index are and what the reference data suggests, we found that Météo-France and UK Met Office models are. So we then use this as a kernel or as a starting point to build a neural network bias correction architecture. And this is sort of like the next bit of the talk, to say, well, okay, you have sort of illustrated the the bias correction framework, not the bias correction framework as yet, but the evaluation framework. But can you design a deep learning or machine learning driven bias correction framework that is that perhaps works in this particular context? And what we do here is first set out what the traditional techniques that have been used in this area are, and often they're often fairly grid specific, i.e. you take a particular location or grid cell in the map below, and then from there you either perform quantile mapping. You take the quantile of your reference data and actually map that to the specific quantile of your model output, and then you've biased in terms of just mapping the quantiles to each other, and therefore if the mappings are essentially quantile to quantile. Another frequently used technique is the linear scaling method, where essentially you learn a linear model. Again, it's going to be on location by location basis. So you're going to, depending on the resolution, spatial resolution of your model, you're going to have essentially, the same number of linear scaling factors as the number of grid points that you have. And this is maybe to also highlight here, this is particularly different from the way we think about deep learning and machine learning, in that those are often operators that take corollaries to image-related sort of fields. So in this particular case, I have a simplified sort of depiction of CSNet, but what we do here is we take the full picture of the region that you're looking at. So it could be in this work we'll actually show outputs for the United States as well as Africa. But you take the full region. You use combinations of two neural network architectures. One is the U-Net architecture, which is essentially a bottleneck architecture that tries to find an embedding of the spatial relationships with a focus on understanding the relationship between neighboring pixels or the neighboring areas in your data set. So essentially, when we talk about pixels or areas in the data set, we sort of have this view of a grid cell of data values. This could be precipitation or temperatures, or any other sort of atmospheric variable that you would have as model output. We think of it even from an image image with multiple channels type of setup. You process that using a U-Net to start with to capture the spatial dynamics, and we do that essentially for each day of the 90 days. But we pass that the encodings, or the sort of like the encodings onto a convolutional LSTM, and the convolutional LSTM is actually short for what is called a long-term, short-term memory network, and this is essentially that tries to carry on the memory or the previous state in a previous time point to the next day, but it's actually infused with newer information. So we have essentially two combinations of neural networks that are operating within CSNet. One is the convolutional LSTM, which tries to capture the temporal dynamics and that are happening from day to day within the season. And then again, we also then think about the U-Net to look into sort of like the spatial sort of combinations that happen. A breakdown of your convolutional LSTM is essentially looking at this. So both of these two architectures that we combine here are quite well used in distinct settings where you're looking for spatial sort of relationships. Particularly, for example, those of people in remote sensing and other fields who probably have used quite a bit of U-Nets. And then if you're looking at time series type settings to capture temporal behaviors, LSTM derivatives are often fairly well used. A simpler version of the architecture that I've just shown is again, you know, at the moment, the network that I'm actually showing here it deals with essentially temperature data. So this is essentially daily temperatures that are being modeled with a seasonal sort of lead time. And then what we then do here is we take again a grid inputs from the physical model. We encode it using the U-Nets for spatial relationships. We then capture the temporal dependencies using the convolutional LSTMs. And once we do that, we do some skip connections that are often to do with regularization of the model. And then we just, again, refine the spatial features with the U-Net, and then we obtain a bias-corrected forecast. The sort of setup parameters here is we have two models that we actually bias correcting here. So when I say respective model data, I'm referring to the Météo-France model and the UK Met Office model. Glossy 5, if anyone knows what the model is. And then we would then use error 5 data as reference. We train between 1993, the bias correction between 1993 and 2008. We validate the models between 2009 and 2012. And then we use the subsequent period post-2013 as a testing period. Moving on to the next slide. Yeah, so some of the motivation, as I've mentioned, is that we're trying to, because of course, when we start looking at grid level processing in the linear scaling and quantile mapping setups, you start having to deal with essentially bias correction at discrete levels, or i.e., you're dealing with each and every grid cell sort of specifically. And the next one is, again, most of those relationships are fairly linear, and then they struggle to capture nonlinear methods in nonlinear patterns in the biases. And then, of course, there is sort of like, again, within the season, there's no sort of temporal, or there's an assumption around stationarity in terms of how those biases would look like as the season proceeds. And those are issues that on the right we try to address in the SeasonNet by using neighboring spatial information with the convolution, the spatial convolutions, and also the U-Net sort of architecture setup, which is very well suited for that. Of course, we're using quite a bit of nonlinearities in terms of activations functions in the neural networks, and the bias correction is dynamic throughout the season. And that's what we said we're motivating season network. And this is the most complicated slide I have here, but this is something that in the context of SeasonNet, we really wanted to address. In that we wanted to, in terms of how the bias correction is learned, it really is a function of the loss function. And the loss function tells the neural network whether it's doing the right thing or the wrong thing. And here we wanted to incentivize our neural network to update the parameters or to train in a way that emphasizes extremes or that emphasizes attention to particularly higher tails of the distribution, higher and lower tails of the distribution. And what we do here is our loss function is a quantile loss function, which is actually quite common in sort of weather applications and sort of like large scale sort of probabilistic sort of implementations of this of these types of models. And what we do there is we calculate essentially the different quantiles between what our model suggests and what our reference data in terms of R suggests. And once we calculate those quantiles, and this is essentially quantile gamma for each of those quantiles, we then say at a particular point in time, for a particular month, we then look at the differences between that, but then we assign weights into how much those differences actually contribute to the loss function. And those differences are sort of exponentially decaying as you move towards the center. So you sort of have them having some sort of a curve that sort of decays towards the center of the distribution and sort of focuses on the different tails of the distribution. And then we often, again, we essentially then sum across the season temporally, and also we sum across the different grids and so on. There's also a fairly sort of simplistic mask that we put in between emphasis on the land and the sea. And we have functionality to sort of learn how much weightings we give to observations over the land and versus the sea, and we often try to bias them to observations over land. So, for example, And this is what I would say a traditional sort of result in a seasonal forecasting setup would look like. This is, if you look at the output over there, the top is you have what is the base model. So here we've got UK Met Office model, we've got the Météo-France model, and this in the African context, we are modeling results over Africa. And then we also have results over the United States and Mexico, North America essentially. And then what we then also look at is we apply the different bias corrections across the different setups. Probabilistically, what we do here is actually looking at higher. This is now the temperature output. So we're looking at higher than normal temperature. So the top tercile on the above distribution, and then we actually look at the Brier Skill Score, which just tells us how good we're doing in terms of identifying sort of like the above normal temperature patterns over the season. And what we see here is if you apply CDNet, it's sort of like the output that you get. If you apply, and this is a relative score on how well we're doing relative to quantile mapping. So it's a skill score rather than just a pure barrier score. And then what this suggests is, the greener you are, the better on the skill score. So in this particular case, as you can see spatially, we have with CSNet SN, this is the linear scaling methods and the quantile mapping methods that are there. If you look at sort of like the tabular results here, they refer to essentially the different IPCC regions within the bigger sort of continental picture. And then what we see here again, the lighter the color, in this particular case in terms of rank, shows which of the models in the different parts actually score well. This is temperatures in the September, October, November, and then we're seeing that bias correction using CSNet gives some utility. And again, another thing that is quite important here is perhaps the resolution of the plot you don't necessarily see, but the sometimes is quite you find limited continuity in terms of particularly with quantile mapping in terms of what the neighboring grid cell says versus the current grid cell, which is the criticism that we've already talked about processing individual cells at a time. So this is just the traditional sort of output you'd see from any sort of seasonal forecasting model. So it just serves as an initial check to see whether we're probabilistically capturing the top tercile correctly. Then when we start looking at warm day frequencies, and again here we will put the threshold at 35 degrees and wanted to see whether again using sort of the seasonal sort of the CSNet bias correction, we would be able to see whether our bias correction actually improves our baseline. Here we're looking at root mean square error on the warm day frequency. So essentially we want to say a bias corrected seasonal model actually then you bias corrects the base models again. But then once you do that, you want to do an evaluation on whether you got the warm days correct in that season. And then again, when you start looking at the root mean square error, so here in this case, you want to mostly look at the lower. So what is almost like the residual bias. So the lower the bias, the better. And again, you start seeing that if you're looking here again, you'll see that our model suggests that you see that although this with again large scale deep learning models, it's not going to be on a 100% basis, but then you actually see that there's some improvement with CSNet when we rank them across the different sort of methods across the different areas. We see that again. Once we apply sort of CSNet on the UK Met Office model, we see improvement in sort of like model rankings. The same sort of does not apply similarly when we apply it over Africa, for example, when we look at root mean square error on the Météo-France model. But however, when you start looking at North America again, you start seeing that you've got quite improvement also looking at the Météo-France model. So there's again quite a bit of interesting investigation that can tell us why, perhaps in terms of process representation in the Météo-France models that perhaps is not capturing particularly some issues in the tropics, perhaps of Africa, that we want to, that we'll be interested in. We do the same again when we're looking at again. Sorry, this is not necessarily warm days frequency. This is actually this is now a warm spell duration index, which is looking at more than so there's a minor typo at the top of the slide, but this at least 3 days where you've got temperatures above 90% of the baseline reference time climatology. And then again, the reference period here again is the reference period that we will look at in terms of the training period and not necessarily in the testing period. And then what we then see here is that the results are a little bit more particularly for Africa, they're a little bit more mixed in terms of what the rankings look like. And again, what you really want to do here is have sort of like the lowest RMSE across the models. In terms, again, as you can imagine with any sort of climatic predictions, once you start predicting spells, which are, or trying to infer spells, which are more persistent events, those are often slightly harder to predict. We seem to be able to do them relatively well in North America, but not necessarily. The results are fairly mixed, but there's some suggestion that if you linear scale Météo-France in Africa, you could slightly have an advantage. So this is another sort of way of evaluating that. And then if we then start looking maybe on the other side of the distribution again, when you are sort of looking at the cold spells, and this in this case, you're looking at temperatures below the 10th percentile. Again, we seem to be able to, again, if this is again root mean square error on the index, we seem to be able to capture that relatively well in areas such as in North America. But again, the model seems to struggle when you start looking into or perhaps performs fairly similar to other competing methods when you start looking at regions in Africa. But then again, in terms of I think overall, in terms of you to calculate a mean or an average across the region, you still find a combination perhaps of season-net and of season-net. And the UK Met Office marginally better. But then in our view, perhaps to then close, I think in terms of seasonal forecasts, we certainly think that they're quite important in terms of the planning horizon that they provide and how such data and understanding of the overall seasonal outlook or seasonal picture could give you in terms of planning. But however, of course, there are significant biases in the forecasts. There are perhaps two ways one could think about it. The approach we've taken here is to take a physical kernel first, so have the input model being a physical model that can then essentially pass on the physics to the machine learning model. Another approach could be if one was to directly look into sort of like rolling out full-on ML models, and that's something that could easily be tested. Then again, we advocate for sort of creating these and augmenting the sort of traditional seasonal forecasting output to looking at different impact-based metrics or indices that allow people to, in different sort of use cases, to actually have actionable insight from what the forecast or the outlook suggests. Season-net is sort of like our proposal in terms of how one would start this. But however, you would want to, and it provides platforms such that you can optimize the loss function that could be perhaps optimized in such a way that captures the intended use case or the dynamics and the bias correction of the output. And then again, the architecture is actually based on a combination of optimal models for spatial and temporal patterns to essentially correct those biases, and with a focus on what we call an extreme aware loss function that we've created. And we've seen that in many cases, we've seen some skill in terms of predicting those warm days and warm spells as well. And again, one of the things that one needs to, of course, look into in terms of next steps or perhaps challenges to extending approaches that are based on deep learning or machine learning would be, the computational costs and versus the additional skill that one gets, and that's something that one needs to again either work in terms of optimizing architecture, looking at different sort of skip connections as we try to, and introducing dropout points and more frequently than not. But then again, also at the moment, our models are trying to look at multi-climatic variables. At the moment, to be honest, the limitation that we have is mainly on the compute side. At the moment, we optimize that in terms of getting our models to fit within the GPUs that we have. We can probably augment our models with quite a few input variables, including that could increasingly enhance skill, as well as give us output in terms of that it's multidimensional in terms of other variables such as precipitation. And that's actually work that's ongoing, and it's exploring a few other sort of opportunities or ideas in the model architecture space as well. That's all I had in terms of this work. I look forward to, this is ongoing work. I look forward to more questions. I look forward to opportunities to collaborate or any contributions that we could have. Thank you so much.
Thank you so much, Dr. Mbuvha, for a really interesting talk. I want to first start with the last point that you mentioned about the high computational costs. Could you talk a little bit about what are the biggest bottlenecks? And if you're moving in the direction of being able to streamline SeasonNet for real-time use?
Yes, so we're not yet, I'll start with the last part because that's the easiest one. And the last part, we're not yet moving into a territory where we would make SeasonNet operational. Again, because it's a function of essentially two things, but operational seasonal forecasting perhaps is sufficient lead time than perhaps weather. But in terms of that, at the moment we're exploring sort of like getting the skill levels in a way that we could justify the additional computation time. And again, the computation time in this case, it scales in the number of compute resources that you have. So in that, at the moment, and I should have had this somewhere on a slide, it takes about 8 hours or so to train. That is not necessarily a big thing, but if you think about it as running on top of an already ran physical model, maybe there's something else. But it's not the most complex architecture to run. But then again, if you think about it in terms of some of the computing techniques that take a few minutes to an hour or so, it's not necessarily relatively competitive in that regard. But the training is one thing. There's always the inference time, which is fairly short. In terms of once you've trained it and you run it, I think we get results in 5 minutes.
And in terms of the implications of these improved bias corrections, what are implications for different sectors like agriculture or energy planning or disaster preparedness? Are you currently collaborating with any end users?
Not at the moment, but there's some interesting projects that we're looking at where we can apply such things by working directly to farmers. And that it incorporates more than just building the SeasonNet architecture as such, but looking into more local data. Because, for example, I mentioned a lot of our reference data is based on error 5. There are known biases in different regions of that data set. And in collaboration with sort of like regional partners, we're looking at training the model on more locally relevant data, and then seeing whether we can get advisories that can aid particularly in agriculture, particularly in African context.
I want to ask about your access to data. I noticed that you said U-Net and Météo-France tend to perform better. What are the implications of given the budget cuts in the U.S. to NOAA, for example, are you at all concerned about access to high quality observational data that models like SeasonNet relies on? How might budget cuts impact this development or validation of these types of bias correction tools? And is there a role for international bodies like the UN, World Meteorological Organization, and others to help ensure continuity of this kind of data given these types of budget cuts?
I will not. I will not. I mean, I've not necessarily have great insight on. What I've found, maybe as a principle, is that the open source nature of public organizations in the meteorological and weather space, in terms of both the tools and making those data sets available, has been a revelation as it comes to the use of AI in this particular area. If you look at the efforts of reanalysis products that like ERA5, I mean, from a seasonal forecasting perspective, models that are coming out of the North American multimodal ensemble that has been hosted by the IRI and a few other institutions have been really, really fundamental to advancing seasonal forecasting over the last few decades. That is certainly quite an important piece of work that, in our view, certainly if it continues, it supports work like our own and so on and so on.
Thank you very much, Professor Mbuvha. I was just wondering, I've been reading a little bit about Google DeepMind's recent release of it's called Weather Next. And I was just wondering if there's any familiar around their model and just how it compares in terms of model architecture and data sources and prediction. If you have any comment.
Yes. Actually, we actually have collaborated a bit with sort of the weather team at Google, and what the Weather Next suite is actually parts of two models. There's a probabilistic models, but both of them are optimized for what is the medium range time scale, which is essentially the 0 to 14-day time scale, which again relies on different sources of predictability to the seasonal time scale models. One of the models is GenCast, which uses which uses diffusion models to actually almost roll out the forecast persistently for 14 days or so. In some discussions with some of the model designers, they suggest that if they roll that on for 90 more days, it remains a bit more stable, and perhaps it could be used in a seasonal context. But at the moment, a lot of the publicly available output is in a 14-day time window. The other sister model in the Weather suite is the GraphCast model, which is again a graph neural network. It takes a different approach to the spatial encodings that we do. At the moment, we're taking U-Net, which is particularly based on convolutions in space. But then the graph neural networks, as the name suggests, tries to fit a graph between different nodes in the data set. It's a direction that has been relatively underexplored in the seasonal forecasting context, and that we're looking at different ways to optimize architecture, both taking inspiration from the diffusion processes as well as including graphs.
Thank you.
Great.
Thank you so much for the insightful presentation. On one of the slides, you talked about impact-based evaluation on densely populated cities across the world. And most cities in sub-Saharan Africa are emerging, and some of them are informal. So what are the differences in terms of performance of these models between these kind of cities, that's the global south and those in the global north?
Yeah, interesting. I wish I had a comprehensive answer to that. At the moment, the evaluations that we did and how we determined the different regions, and there's probably different ways we could have done this, is we actually used modest data. So we use satellite imagery to tell us where the people are. And I think if you saw in the slide, it suggested that people are, really the evaluations were mainly centered around Asia. But you're right. It's probably quite interesting to start looking at, how the emerging cities in Africa would suggest. And of course, the satellite data, it was based on light intensity. So in terms of how you sort of want to do that, would differ in terms of the jurisdiction. But so at the moment, our sort of impact, most of the sort of highly densely flecked areas were in Asia. But interesting sort of observation in terms of what that could look like over Africa. And it will be I don't have a result. We can have one, but not today.
Thank you.
Wondering if you could talk us a little bit about what's next for SeasonNet. Are you exploring using it for subseasonal forecasts or maybe decadal predictions? And also how generalizable is your model to other variables beyond temperature?
Yeah, so the last part is the first point in terms of our next steps. It's generalizing to precipitation because it's the hardest to model, but it's the one everyone needs. And that's something that we're working on, and we're trying to use different data sources because it's also difficult to measure, and we're trying to triangulate that. So we're trying to use a few other meshed products other than ERA5 because there's some issue spatially, and there's some literature that suggests that the rainfall fields are heavily biased on ERA5. So that's the main thing. That also coupled with sort of architecture updates that are following on to the state of the art, such as the earlier question mentioned. So including graphs, including if they provide scale, as well as diffusion, as diffusions. But the next thing that comes on, and this is more on a route towards sort of operationalization, is we're talking to sort of agricultural research entities in the global south, particularly in Africa, where we're going to try and embed that data into the framework and see whether, again, in a controlled manner through verification, whether SeasonNet can actually provide superior seasonal forecasts to the forecasting systems that they have.
So could you talk a little bit more about what that process might look like and what, I guess, an ideal outcome for you would be?
Yeah. Okay. So in terms of the ideal outcome for us is, I come from South Africa. There are about 4 million farmers in South Africa, particularly on the informal side. What we are sort of keen on is, the downstream sort of task is one, seasonal forecasts are a little bit difficult to ingest because people come with the trials that I was talking about and things like that. But we want positive outcomes, but also positive sort of in terms of improvements in yield. And again, this could eventually, in my world, but I'm sort of cautious about that, is lead to better understanding and pricing of parametric insurance. Because if you think about the idea of being able to model the season correctly, and they often sort of again, financial inclusion products and other things that support resilience of farmers on the basis of that, you could improve the pricing, and then by that very nature, you improve the price points. But that's the more downstream task. But the idea on us is more like you get the focus correct, such that the advisories through the right agrometeorologists, getting to the farmers. And we're working with the Agriculture Research Agency in South Africa, Research Council in South Africa, to actually do that. But we're fairly early stages in that project in terms of getting that done. The approach we're taking there is a co-creation one. We want to find out where the farmers are in terms of seasonal forecasts. What do they use? There's a mixture of, particularly in the informal sector or the subsistence farming sector, there's a mixture of indigenous knowledge and sort of using forecast products. How does that? So it's going to be a fairly the SeasonNet is but one component of that, but understanding the process such that with some abstraction, it can have utility for the relevant community.
Oh, thank you so much. I think the focus on co-creation and applying it in the field and this really, context-specific research is something that I think really resonates with a lot of us here, and we're looking forward to following up as you continue this process and learning more about your next steps and findings.
Yeah, thank you so much. If anyone, I think I see Martin at the back, or Martin at the back there. If anyone wants to sort of reach out to collaboration, I'm very, very keen to work with anyone in this work or its implementation.
Thank you. Thank you so much, Dr. Mbuvha.
Thank you so much. Thanks.
Thank you to all of you for joining us. We look forward to welcoming you again next week. And thank you again, Dr. Mbuvha. We will see you next week.